In section 6 of chapter 10, we are now going to be utilizing our knowledge of logarithms as operations to solve problems for parts that previously were unsolvable. Before I do that, I want to remind you of the two equations that we did last chapter that deal with exponential growth and decay for compound growth problems and continuous growth problems. As a reminder, compound growth primarily deals with finances, with money, because those things will grow at set intervals, as opposed to continuous models, which largely reflect nature, things that are always either growing or decaying. Like a tree that falls in the woods is always losing mass, or radiation is always just slowly decreasing over time after radioactive exposure. Now that we know logarithms, we're going to be able to start solving for things in these equations that we typically would not be able to solve for. In the past, I would tell you, like, hey, you have an initial amount of $500. You're investing it into an account that grows at 7% monthly, and it compounds daily. And we're going to leave it alone for 8 years. You'd be able to calculate how much money you'd have at the end of that period of time. If you think about finances, that's typically not how finances work. Typically, you know how much you are going to be investing. You will know how much, or the rate at which it's going to be growing. You'll know how frequently it's going to compound. The variable that is unknown is how long you're going to leave it into that account. But you might know, oh, I want to pull out this investment once it reaches $10,000. Typically, we know the initial amount and the final amount. Typically, the part that we do not know is time. Time is typically the variable when you're dealing with this in the real world that is going to change. Are you going to leave it in there for 3 months, 3 years, 3 decades? So we need a way to solve for t. The way we do that is using logarithms. So this last chapter where we were kind of messing around with this, the main purpose was so that we could get here and start using logarithms to solve for t. Now, for compound equations, like the one in the first problem, it will help you solve for t. It will not help you solve for n, because n is in 2 locations. But for continuous growth and decay problems, it'll help you find t and also k. What that means is if you have a model, you can also relatively figure out the rate at which something is growing or decaying, which can also be very good in certain circumstances. So, problem number 1. I have an initial amount of 250. That's my C value. So 250 times the quantity of 1 plus my rate of growth, my K value. It is a monthly rate of growth of 7.1%. So as a decimal, it's growing, so it's positive 0.071. I am compounding daily. I need to ask myself, how many days are there in a month? There are 30. That'll be raised to the power of the n value again times t. I do not know how long I want to leave this money into that account. But I do know that once I leave it into that account, I want it to end when I have $1,200. Now, in the last chapter, I had you stop here because typically in the last chapter, I had you solve for y. Y was already isolated. It was already set up as y equals crazy complex expression. I now want you to solve for t. T is a part of that equation. So we can't stop here. We got to solve for t. Now the way I'm going to do that is I got to get rid of everything on the right side. So I'm going to divide both sides by 250, allowing these to cancel. I'll simplify this a little bit. That is 120 over 25 is equal to 1 plus 0.071 over 30 raised to the 30 times t power. Now that I have the exponential portion isolated, I can use my conversion process to turn that exponential into a logarithm, because what I want to solve for is an exponent. So I'm going to convert it using our conversion process. A to the b power is equal to c can convert into or convert from log base a of c is equal to b. So for this problem, this is going to turn into, it's not going to look pretty, but it is going to be correct. Log base 1 plus 0.071 over 30 of 120 over 25 is equal to 30 times t. Last thing I need to do is get rid of that 30 in front of the t, so I'm going to divide both sides by 30. And that'll give me t is equal to log base 1 plus 0.071 over 30 of 120 over 25, all divided by 30 as my final answer. Problem number 2 is slightly different. I will tell you right now, continuous growth problems are so much easier. You're still going to do the same math, but because the inside parentheses bit doesn't exist for this problem, the 1 plus k over n is just now going to be an e. That'll make this a whole lot simpler. Problem number 2, I have 50,000 cells. I want the final amount to be 100 cells, so I went from 50,000 to 100. That means I'm decaying, I'm going down. So I know this is going to be a decay value. The hourly rate of decay, notice it says decay, is 13.8%. I want to know how long am I going to leave it for it to go from 50,000 to 100 cells. So in my equation, that's going to be, I started off with 50,000 cells. It's going to be times e to the rate of decay, which is negative because it's decay, 0.138 times t, because I don't know how long I'm leaving it, and that's going to be equal to 100. The process on how I solve this is no different than problem number 1. It's just the numbers work out a little bit nicer. Divide both sides by 50,000. Those will cancel, and you'll get 1 over 500 is equal to e to the negative 0.138 t power. Now I have a number equals an exponential. The variable I'm trying to solve is an exponent, so I have to use logarithms. I'm going to convert this from exponential form to logarithmic form. Natural log, because the base is going to be an e, of 1 over 500 is going to equal negative 0.138 t. Divide both sides by negative 0.138. These will eliminate, and I will find that t is going to be equal to the natural log of 1 over 500. All divided by negative 0.138. That will tell me how long it will take those 50,000 cells to turn into 100 cells. Now, because the rate is in hours, this unit of time would also be in hours. But I'm not expecting you to write this as a sentence. Just give me that answer and we will call it good. This is how we solve for our variable exponents using logarithms.